Hi everyone, this is Mr. Bozade, and I'm going to talk us through this bucket weld problem in which we have a 4 kilogram bucket that's attached to a 40 centimeter diameter pulley. Assuming that the string doesn't slip and the pulley is a solid cylinder with a mass of 1.5 kilograms, we are going to right now find the acceleration for the bucket as it falls. The first place to start, which I recommend always, is drawing free body diagrams. So right here I've started to draw my free body diagram for the bucket, and of course the bucket feels force gravity on it. As it falls in, it also feels force of tension. Notice I've made force tension smaller because the bucket's accelerating downwards, so gravity must be greater than force of tension. Now let's draw the free body diagram for the cylinder that the rope is wrapped around. And of course the cylinder's got force gravity on it, pulling downwards. It's also got force tension pulling down on it because the rope is connecting the bucket directly to the cylinder. Those two force tensions are the same. And the cylinder also has a force normal pointing up. And that force normal I've drawn larger because it would be balancing force gravity and force tension in the y direction. For the pulley, we are going to be applying net torque equals I alpha because the pulley will be rotating. And for the bucket, we will be applying net force equals ma because it will be translating, moving in a translational motion. The first thing we want to do before we really jump into either of those equations is think about positives and negatives. So the pulley is alpha-ing, or rotationally accelerating that way, which is counterclockwise, and the bucket is accelerating translationally downwards. Since they're doing these things together, in other words, the acceleration of the pulley and the acceleration of the bucket are really the same, or they're accelerating together, we want to make them both positive. So I'm going to say counterclockwise is the positive direction rotationally, and downwards is the positive direction translationally. Then we can write out our net torque equation. That means torque of force tension is positive because it's counterclockwise. Force normal and force gravity are both not applying a torque to the cylinder because they are at a radius of 0. In other words, they're acting right at the axis of acceleration. And so we'll set that equals to, that torque of force tension is equal to I alpha. And in this case, we're going to choose 1/2 mr squared to be our I, our rotational inertia, because the problem says this is a solid cylinder. And for the bucket, we've got plus force gravity minus force tension equals ma, or the mass of the bucket times acceleration. And as I mentioned before, we'll see downwards is the positive direction because the bucket is accelerating downwards as the cylinder is accelerating counterclockwise. From there, we can elaborate a little bit on both of our equations. Instead of thinking of it as just torque of force tension, we'll think of it as radius times force tension, and force gravity known as mg. Good thing to do at this point is to check in on how many knowns and unknowns we have. We obviously have two equations, but we have more than two unknowns. Here we've got force tension that is acting on the pulley, and here we've got force tension that is acting on the bucket. But as we discussed earlier, those are the same. So we've got one unknown there. Alpha is an unknown. In other words, the rotational acceleration of the pulley is an unknown, and A is an unknown. In other words, the translational acceleration of the bucket is an unknown. So we have three unknowns, but only two equations. We need to try and figure out a way to get two unknowns if we have two equations. Well, one way we can do that is we can work with this alpha. We know that if we think about a point on the outside edge of this pulley, it is its tangential acceleration, or translational acceleration, if you prefer to call it that, is equal to the translational acceleration of the bucket. So we know that we can find the tangential acceleration for a point on the outside edge of this pulley by using our bridge equations, or dividing alpha by radius, the radius on the outside. If we do that, then this net torque equation, we now see that alpha is A over R, and we now see that we only have two unknowns. Again, force tension counts as 1, and acceleration on the outside edge of the pulley at this radius, which is the radius to the pulley, is the same as acceleration, translational acceleration of the bucket downwards. So now we have two equations and two unknowns, and so we just have to substitute and solve for one of the unknowns. Our goal in this problem is to solve for the acceleration of the bucket, so we're going to substitute force tension over and find that acceleration. We can simplify our net torque equation by dividing the radius over, so this now becomes r squared, and we see that the radius cancels out because this is the radius of the rotational inertia equation, which is 1Fm r squared. That is the outside, or the outsidemost radius of the pulley, and this is the radius that the acceleration that we're considering the tangential acceleration of is, which is the outside edge of the pulley, and this is the radius where the force tension is being applied, which is at that same radius as well. So in all three of these situations, that r is the same radius, radius to the outside edge of the pulley. Again, this is the radius where the point on the outside edge of the pulley is experiencing tangential acceleration equal to the acceleration of the bucket. This is the outside edge of the pulley because it's the radius that's associated with the rotational inertia of the pulley, and this is the radius where the force tension is being applied, which is also on the outside edge. So we can cross out the r squareds, we can combine them and simplify them so they cross out, and simplify this force tension. This net torque equation simplifies to just force tension equals 1/2 mass of the pulley times acceleration. One thing I should mention is that earlier on this step here, I added some coefficients to the masses so that we could keep them straight, because when we do our substitution now, we're going to have different masses, and we want to not mix them up. So, for example, we're going to substitute this in, 1/2 mass of the pulley times A, in for force tension. And now our net force equation becomes this right here. The next thing we need to do is we need to, because our goal is to find acceleration, translational acceleration, we're going to move this to the other side, add this to the other side, so we get all the acceleration terms on the same side. Then we will factor out the things in front of, or I should say, we'll factor out acceleration, like so, and by doing that, our net force equation simplifies to this. And then finally, to solve for acceleration and isolate it, we will divide this to the other side. So our final equation for acceleration looks like that. Mass of the hanging, mass of the hanging mass, which is why I put an H there for the bucket, times gravity divided by the hanging mass of the bucket plus 1/2 times mass of the pulley equals the translational acceleration of the pulley, of the bucket, as well as the tangential acceleration of a point on the outside edge of the pulley. So let's plug in our values. The bucket has a mass of 4 kilograms, and the pulley has a mass of 1.5 kilograms, and we solve for our translational acceleration, and we find it is 8.25 meters per second squared. There you have it. I would say some important steps that we looked at here today are figuring out how to turn our unknowns so that we have two unknowns for two equations so we can do substitution. And the key to getting two unknowns was using our bridge equation. After we did that, another key thing that we talked about was how in this problem, all these radii, this one, and this one, were all the same. Another key thing that I would say we did was we then saw how we substituted our force tension from one equation into another, and by doing that, we only had one unknown, acceleration, and then we just did a bunch of algebra so that we could solve for our acceleration. There you go. I hope that's helpful, and I will talk to you another time soon. Bye.